Welcome back to The Explainer. Today, we're zeroing in on a completely critical, but let's be honest, often totally overlooked piece of commercial and industrial construction, the perforated cable tray. Now, if you're an engineer, a project manager, or you design facility infrastructure, you already know these systems are the absolute backbone of your power and data networks. But based on the latest data we're seeing, selecting and sizing them, it's actually not quite as straightforward as it seems. Let's dig into what the guidelines are actually demanding for upcoming projects. So I want you to ask yourself honestly, are your 2026 project specs getting cable tray sizing entirely wrong? I know, it sounds like a pretty bold question, but the reality is, despite this being a literally fundamental system in modern construction, a staggering number of engineering specs are still relying on massive calculation errors. We need to figure out exactly why that's happening. Okay, here's the game plan for today. We're going to cover 1. The sizing mistake, 2. IEC 61537 load classes, 3. Perforated versus ladder trays, 4. The 3-step sizing method, 5. Selecting the right material, and 6. Intelligent solutions by Xinma. Let's get right into it. Section 1. The sizing mistake, a costly oversight.
Okay, let's dive into this. Relying on outdated sizing assumptions is honestly a silent project killer, especially in dense, high-stakes environments like modern data centers. The perforated cable tray is, without a doubt, the most widely specified cable management system in construction today. Yet, paradoxically, it is the system with the absolute most sizing errors. Why? Well, because they are so ubiquitous, there's this really dangerous tendency to just sort of copy and paste older specs into new 2026 blueprints without actually running the numbers for modern cable densities.
Moving on to Section 2, IEC 61537 load classes, beyond the headline. And that brings us right to our first major technical hurdle. The IEC 6057, this is the critical global standard defining cable management system performance. Now, usually you'll see a load class defined by a specific kilograms per meter capacity, right? But here is the catch. If you are only looking at that basic load rating, you are making a massive mistake, because that headline number, it's really merely a starting point. That's right, the kilograms per meter figure is literally only half the story. Look, a single capacity metric isolated on a piece of paper doesn't magically guarantee real-world safety once the system is actually suspended up in the air in a bustling industrial plant. You absolutely have to account for the physical realities and the actual stresses of the installation environment to truly understand what that load class means for your specific structural layout. Section 3. Perforated versus ladder trays. An 8-parameter comparison. Now, what's really interesting here is that before we even touch the math on sizing, we have to select the correct baseline architecture. While standard comparisons look at up to 8 different parameters, the most critical differences really just come down to structure and application. Ladder trays, they are excellent for heavy, single-run power cables because of their open-rung structure. Perforated trays, however, give you a continuous base with ventilation holes, and real project data consistently shows that this continuous support makes perforated trays the far superior choice for massive bundles of smaller, flexible cables. You know, like the dense data networks routing through high-tech commercial buildings. Which leads us to Section 4, 3-step sizing method, the exact formula. To totally eliminate the guesswork from the engineering workflow, here is the exact standardized formula you need to be using. Step 1, execute a comprehensive cable area calculation for all the wires in the run. Step 2, apply a strict 40% fill ratio to that calculation. And Step 3, use that resulting total to make your final tray width selection. Follow these exact steps sequentially, and I promise you, your sizing will be mathematically sound every single time. And this brilliantly illustrates why Step 2 is so absolutely crucial. The math here is completely non-negotiable. Limiting the physical cables to just 40% of the tray's cross-sectional area leaves you with 60% empty space. But listen, that is not wasted space. It is absolutely vital infrastructure for heat dissipation and airflow. If you try to pack a tray to 100%, you are not building a data network. You are essentially building a very expensive, very dangerous space heater. Without that 60% airflow, cables overheat, performance bottlenecks, and safety tolerances are completely thrown out the window. All right, Section 5, selecting the right material, beating corrosion. So we've mastered the sizing math, right? But the harsh reality of construction is that even a perfectly mathematically sized tray will absolutely fail if it's manufactured from the wrong material. Standard commercial offices might do perfectly fine with hot-dip galvanized steel or aluminum, but if you're routing cables through, say, a harsh chemical plant or a highly corrosive marine environment, you're going to need the heavy-duty resilience of stainless steel or fiberglass reinforced plastic to prevent the entire system from degrading. You just have to correctly match the material to the specific environmental challenge you're facing.
Next up, Section 6, Intelligent Solutions by Xinma Meeting the Standard.
When we actually look at the execution phase, like who is out there producing materials that genuinely meet all these rigorous demands, Shanghai Xinma Busway and Cable Tray really emerges as a gold standard manufacturer. Navigating all these structural and environmental complexities, their intelligent cable management solutions, busways, and seismic bracing are heavily utilized across the most demanding sectors. We're talking state-of-the-art data centers, incredibly complex rail transit systems, heavy-duty industrial plants, and massive high-rise commercial buildings.
So the crucial point is what makes all this work in practice: strict adherence to global compliance. Xinma doesn't just build to an estimate. They adhere to an incredibly rigorous list of global standards. This includes the international IEC 61537, North American NEMA standards, European BSEN specs, and Chinese GB national standards. Having this massive global certification footprint ensures that when you actually specify their trays, those headline load classes and material specs will genuinely perform exactly as calculated. We've covered the load classes, the absolutely essential 40% fill ratio, the critical material differences in the manufacturers actually setting the global standard. So, as you look at your blueprints today, I want to leave you with this final thought. Are your upcoming 2026 project specs rigorously engineered to meet the standard, or are you just sort of guessing and hoping for the best? Seriously, don't leave your critical infrastructure to chance. Run the calculations, demand the correct materials, and build it right the first time. Thanks for joining me on this explainer, and I'll catch you on the next one.